Hello, this is TA Eunbyeol. Please make sure to download this material from Classroom. Today we will cover Variational Autoencoder, practice with PyTorch. The main points of today's practice are understanding and implementing the model architecture and the loss function of VA. This practice will be very similar to the previous autoencoder practice. So I hope you guys are familiar with the basic concepts of autoencoder and code implementation. The variation autoencoder is quite a bit more complicated than the autoencoder. I hope you remember the VA lecture from this Tuesday, because today's exercise heavily relies on that knowledge. Now let's begin with our Jupyter notebook. As I mentioned, the VA is based on autoencoder, thus we will slightly make changes in the implementation of the previous code. First, import some packages. Among them, there is one additional package introduced this time called makeGrid. The makeGrid is supported by torchvision.utils. It helps us make grid-style figures from multiple images. We'll use it soon. And let's set the hyperparameters, which is similar to the previous practice. Yeah, batch size is 128, and learning rate and number of epochs. Oh, I think. Okay. Oh, this is solution. And the second step is the data preparation. It is also the same as previous practice. We will split the training data set into training and validation sets in a random manner. And note that validation split is only used to evaluate if our network is well trained or not in terms of loss observation. And also, remember, to shuffle is true for the training data loader, right? Run this code. Now, let's move on to today's main interest. The overall structure and process of a VAE are presented in this figure. I'm going to quickly review the core difference from the autoencoder using this illustration. Similar to autoencoder, we feed input X, and compress image into a latent vector. And this latent vector is then decoded to generate images, which should be identical to original images. This is the same part. But unlike deterministic encoding in autoencoder, the VA encodes input images in a stochastic manner. This is the key difference from the autoencoder. So in other words, the encoder tries to represent the input image into a Gaussian distribution characterized by parameter mu and standard deviation sigma. In this way, the encoder and decoder are not only trained to reconstruct given images, but also to make latent space follow a Gaussian distribution. Here, the beauty of a VAE lies in its ability to guide the latent space towards a Gaussian distribution. These features of the VAE enable it to generate images that are distinct from one it has trained on. In other words, you can create entirely new samples, new images, by sampling Z from this Gaussian distribution, unlike autoencoder. Okay. Different from this complicated concept, actually, the implementation of VA is quite straightforward and very similar to the autoencoder. So we will implement the VAE with this input, its amnist, and output, this description. And to restrict the model power, we use one hidden layer here. Actually, two. Okay, encoder is one layer, yeah. The different thing we consider is the sampling process, which encodes image into mu and log variance. We will use log variance. So this is main difference from last week. So I'll give you 5 minutes. Please implement the init method in the Variational Autoencoder class. After 5 minutes, we'll go over the answer together. Let's get started. Just implement this part. Okay. Okay, time is up. The answer is yeah. Yeah. While the encoder and decoder may seem straightforward, you might be curious about the role of FC mu and FC variance. Similar to encoder function, both of these layers produce 10-dimensional vector, right? But if you delve into the forward function, it becomes clear that both mu and log variance fit into the reparameterization function, which in turn samples the latent vector z. This latent vector z will be used to reconstruct the image, which are similar to the input image. Then what is the reparameterized method, and why do we use it? We won't cover the detailed explanation about this in this practice, but in a nutshell, this is for making the encoder part as stochastic and enabling the use of backpropagation to optimize the objective, right? So now you can implement the reparameterization trick here. I'll give you 5 minutes. Implement this blank by yourself. Okay, time's up. The standard deviation is easy since it's just math. And how about epsilon? Epsilon is kind of noise, sampled value from a normal distribution, and which has the same size as the standard deviation. So the answer would be like this. Yeah. I think it is clear. And the main other part of the implementation is the loss function. The loss function of the autoencoder was just a simple MSE loss to measure the difference between the original image and the reconstructed image. Yeah, check the device. And similar to that, VA's loss also includes a reconstruction loss defined by binary cross P entropy loss. By binary cross entropy loss can be easily computed by using PyTorch module like this. And we'll use the summation reduction mode to make implementation easier. Okay. This is for PC loss. And the other loss part is the KL divergence loss, right? Which is a regularization term to make the posterior distribution similar to the Gaussian prior. You may unfamiliar this equation, but since we assume the two distributions to be Gaussian, we can compute the KL divergence in a closed form. It's like this. Please make sure you can fully understand and implement this part by yourself. Okay. We are gonna init the Variational Autoencoder class and use Adam optimizer. Since we already dealt with this part from the previous session, the training code is fully implemented, and it's almost the same as the previous autoencoder practice. But the difference may be we do not multiply batch size here, since we calculate loss in this way. So it includes the batches, it is multiplied by batch size. So yeah, maybe difference. Maybe this is only difference. Oh, no, of course. This part and this part would be different, yeah. So run this training code. It'll take about 1 or 2 minutes. Yeah, can wait. Let's wait. Oh, okay. Standard deviation part. I'm sorry. Standard deviation is defined like this. Since our layer outputs the log variance, so we need to exponential the log variance and multiply this, yeah. Minte, is it okay? Okay. Did you guys finish the training? You can easily check the results with this rules plot. As you can see, VA is trained well on the MNIST dataset in terms of loss plot. Yeah, it can generalize well on the test image. Why do we use log variance instead of variance? It doesn't matter, but you can use variance here. Oh, where? I'm sorry. You can use variance here, but just make sure standard deviation always be positive, always bigger than 0. If you use log variance, it is hardly make mistake. But you can also use output variance too. Okay. Yeah, it doesn't matter. The log metric variance can range from negative infinity to positive infinity, which provides great flexibility in the variance distribution. Oh, yeah. Oh, thank you for good insight. Yeah. Thank you, Sung. Okay. Great. Yeah, I will read material. So let's move on. Another qualitative method to assess our VA is through the visualization of the encoded input images. As plotted, 1, 2, 3, 4, 5. Yeah. 5 digits are the trivial case of digits 1 or 4 are reconstructed well. But the number 3 seems to be mistaken for 8, right? Yeah. And another visualization, it is the same as the last session. Please just run this code. Yeah. Yeah, because we just one hidden layer to encode the input image to mean and variance. Yeah. You're right. And we're gonna do VA with higher capacity soon. And you can compare the performance between the VA with higher capacity or low capacity. Yeah. And as plotted, 10 digits are separated quite well on the feature space with a trained VA encoder. Those two evaluation methods are already presented in the previous practice. So let's move on. The third evaluation method, is generating MNIST images only from the sampled latent vectors. Such outputs can't be produced from the autoencoder, since the autoencoder does not guide input image into a predefined prior space, right? So it is interesting to observe how the generated images can change through the latent space traversal. Okay, let's leverage the encoded feature vector of a trained dataset. This encoded is from where? Here. Yeah, this is from trained data sets. We're gonna average this feature vector. Since we already checked that we successfully encoded each of digits and they are separated well in t-SNE plot, so we just calculate the mean feature vector of each digit from the encoded feature vectors, like in this code. Yeah, please just run this code. Then we explore the latent space between two digits mean feature vectors. Let's take two cases like 1 and 7. It is very trivial cases. What? No. And run this one. As you can see, while traversing between those two mean feature vector, the generated image transforms transition smoothly from 7 to 1. And a similar smooth transition is observed from 8 to 1, right? This shows the effectiveness representation of each digit in the latent space and the powerful generation ability of the VA. We just interpolated this latent space, right? And move on. So do you have any questions? Yeah, cool. As earlier I mentioned, this is also VA architecture with larger capacity. You can easily implement this code, okay? Just, yeah, implement this code, please. I'll give you 5 minutes. It's just recap, yeah. Let's get started. Okay, time is up. The answer is here. Yeah, of course, 784 and 512 and 512, and yeah, it is much more higher. Okay. And this is obviously the same part. And yeah, nothing special. Just, sorry. It's just the architecture with larger capacity, so you can easily implement this code. And please run this code. When training is done, we can compare the effectiveness of model capacity in terms of the quality of image reconstruction. Okay, please run this code. Yeah, I assume your training is done and it trains well. When compare high model and low model, the model with higher capacity is lower than the model with lower capacity, right? And also, when run this code, we can see variation autoencoder with a higher capacity reconstruct the image better than the lower capacity variation autoencoder, right? But yeah, it is quite blurry, but it is more clear with a higher capacity, and it looks more like 3 than this. So as Song said, the middle column is not look good, but it looks better on the third column. A natural question to pose it, what if we draw Z straight directly from a standard normal distribution until we extract Z from a training set, not a random normal distribution, right? How about this? Considering that our VA's posterior is tailored to approximate a Gaussian distribution, in theory, we should be able to draw samples directly from this normal distribution. So when we visualize 100 generated samples, the digits appear somewhat unusual, but yeah, they retain recognizable characteristic of digits, right? Still bad, yeah. But we can recognize this 8, 3, 7, 5, right? This is our last part. Regarding this figure, I should modify the title. My apologies for any confusion. I prepared this content based on material from last year, but I think this figure is not related to BC laws and MSc laws. I read this paper. You can search this paper. I think this figure is not related to BC laws and MSc laws, but the author wants to say why variational inference is needed through this figure. This figure looks like this. Let me explain briefly. We typically assume that Z comes from manageable distribution like normal distribution. And based on this, we undertake the sampling process. So one might ask, when training, can we just sample from this Gaussian distribution and generate new data, and then directly compute MSA laws against the original data? The short answer is no, because the reason becomes evident when considering this case, this figure. Let's call image A is our data X, and image B is a version with the front part is cropped, and image C is shifted by a single pixel to the right. Semantically, we all know A and C should be identical, but in practice, MSE between A and C is greater than A and B. As such, when we sample from the prior PC, when training, issue can arise. So given these challenges, rather than directly sampling from the prior Z, it is proposed to sample Z based on X. But this ideal sampling function P, Z given X, remains elusive. So we learned what is variation inference in the class. So we're gonna use variation inference, bring a simple distribution QZ, and aim to use QZ by approximating it into PZ given X. Yeah, I hope you can understand what I'm saying. And in short, this is the theoretical part and kind of irrelevant to today's practice. So if you're interested in, please read this paper. It's well written. And yeah, all right. I think that's all for today's session. Do you guys have any questions so far? Oh, there's a lot of questions. Oh, okay, wait a minute. Could you explain why such simple view variance respectively? They have different semantics, isn't it? I can get it. What's your point, Hyungchan? Can you give more detail? And Jae-sung, could you explain MP where terms in MP? Okay. You mean traversal part, right? Yeah. Let's see. There's a labels, and when labels are 0, we can index this encoded part, right? So we aggregate some specific number and get the mean of the feature vector to interpolate, right? We want to interpolate mean vector of 1 and mean vector of 7. So we just aggregate all 1 or one encoded vector and just average in the sample-wise, axis 0. There's one question. Okay, Ardo, is this way we use adversarial laws as well for VA currently? Yeah, maybe there are already a bunch of papers using adversarial laws in VA. Yeah, I think you can find easily. Did you understand did you understand? And Udong, in the reparameterization tree part, can you explain why code is? Oh, this is just, wait a minute. Yeah, because we calculate variance in log form, right? So when we get the standard deviation, we have to we need explanation. In this code, get the image generated from the latent space when we given 2 and the values 1 to the distribution. In this code. Suji, do you mean why we use interpolation here? Okay. Since we force the posterior distribution in some Gaussian distribution, right? So as you can see, if these digits are in the manifold, we can the model learn to how to generate the image, but also learn the real latent distribution. So we can manipulate on that distribution. So one representative example is interpolation. And one Trevor, could you explain again why such simple mu syndrome? 민 베리언스 의미하도록 뭔가 다른 함수를 씌워놓지 않아도 되는가? 그러니까 지금 가우시안 디스트리뷰션을 가정하고 있기 때문에 가우시안을 파라미터라이징 하는 게 결국에 민이랑 베리언스 2개로만 결정이 되니까 그 2개를 가지고 하는 것 말고는 사실 가우시안 디스트리뷰션이라고 가정했을 때 이 2개 말고 다른 걸 사용하기는 좀 어렵지 않을까 싶습니다. 형자님 네, 잘 대답이 됐을까요? Okay. All right. I think that's all for today's session. Yeah, I hope you enjoyed this practice. Minte, you too. Thanks for your participation. Really appreciate your participation, even though it is Chuseok. And I'll see you in the next session. And happy Chuseok. Yeah, thank you.